Hi everyone! In today's video I would like to show you how to make a planetary gear set, which will allow you to transmit high amounts of torque at a relatively high ratio in a very compact package. I would like to start today by showing you how to model the red ring gear. I'll do it once first to show you the basic idea of how to do it, but it will lead to a few inaccuracies, so I will do it a second time to show you how to correct for those. Starting from an empty file, the first thing I'm going to do is create a gear with the same parameters that I want for my eventual ring gear. So metric with a 20-degree pressure angle. I'll take a module of 2 mm with 56 teeth. I'll leave the backlash at 0 to show you the inaccuracies later on. A root fillet radius also of 0 for now. I'll make it 20 mm thick and I don't want a hole. So there we have a gear. And now I'll activate this new component and create a sketch on this top surface here. And then I'll hit C for circle, and let's just make this 126 mm in diameter. Finish the sketch, E for extrude, and I'll select both of these profiles. And then I'll drag these down by minus 20 mm. And I'm going for operation new body. Click OK. And once that's done computing, modify combine, a cut. The target is the large cylinder, the tool is the gear, and then you can click OK. And then under the spur gear component we'll have one body left, and that's our ring gear. I want to show you how this ring gear interacts with a regular gear, and for that I first want to create a supporting bracket. So I'll activate the root component and create a new component that I will call bracket. And then I will create a sketch on this bottom plane here. Make a circle of, let's say, 100 mm. And then I'll make another circle that is 19.5 mm. And I will ensure that that thing is vertically above the origin and that it is 36 mm above the origin. Then finish the sketch. And then I'll extrude the main bit 3 mm upward. And then I'll unhide the sketch and extrude this bit 20 mm upwards. We can now set up our first joint, so I'm going to hide the sketch, we no longer need it, and activate the root component. And I'm going to right click the bracket and select ground so that it can no longer move. And then I'm going to create a joint. I'm going to the underside here, and I want to join this ring gear, so I hold Control so I can select the center of the ring gear, and I'm going to join it to the center of the bracket. So it's the good revolute joint right now, so I'm going to flip it up, and then I'm going to press animate to double check that it's good, and that looks pretty good. The next thing I'm going to do is create the pinion gear that is supposed to mesh with this thing. So I'm going to create a spur gear, and I'm going to create it with 20 teeth, and I'm going to give this one a hole diameter of 20 mm. And then I'm going to create a second joint, which is a revolute joint between this pinion here and this little shaft nub over there. I'm going to flip this and just animate it again to be safe. And that looks pretty good. So now our joints are set up, and now we need to set up a motion link. Before I do that, I would first like to give some names to my joints. So if I look under joints here and I click this one, I see that it is this joint in the center. So I will call that ring gear, and then the other one is the revolution of the pinion. And I do this because the order in which I click these joints matters. So under assemble we go to motion link, and I want to link the rotation of the ring gear to the pinion. And then I want to ask myself, if I rotate the ring gear 360 degrees, how much does the pinion rotate? Well, the ring gear had 56 teeth and the pinion had only 20. And of course the pinion would have to turn faster than the ring gear because it has fewer teeth. So if I just take that gear ratio and multiply it by the same 360 degrees, we should get the right ratio. And if I reverse this now, you see that it indeed matches up. Now that we have the motion link set up, we can take a closer look at how well these gears mesh. There will be a little bit of interference here, and I want to make that more obvious by creating an offset plane off the top of this ring gear. Just drag this down a little bit and then do a section analysis on that new plane. And then I'm going to hide the plane, and then these colored hatchings will better show the interference. So if I now zoom in, we see first of all that the fit here is extremely tight, and this is because we selected 0 backlash on both of the gears. But if I rotate this orange gear a little bit now, we see over here that these two lines are sticking into each other. So here we can see them intersect, and this is a little bit of interference now between the pinion and the ring gear. The second issue, if I rotate them back a little bit, is that the outer diameter of this pinion here sticks all the way into the inner diameter of the ring gear. And if I rotate them one tooth over, then we see exactly the same problem with the tooth of the ring gear going all the way into the trough of the pinion. Now if we look at the meshing of a regular set of spur gears, we see that that's not supposed to happen. So there is a little bit of clearance here between the tooth tip and the trough of the mating gear. The problem here is that if we look at the pitch diameter or the pitch circle of this left gear, we see that it has a radius of 30 millimeters, and the outer diameter has a radius of 32 millimeters. So between this circle here and the outer diameter, we have a total distance of 2 millimeters. But this inner diameter over here is almost 2.5 millimeters smaller than this 30 millimeter circle. So here we have the addendum of 2 millimeters, which we've discussed in video 4, compared to a dedendum of nearly 2.5 millimeters. But what happened is, when we did that combined cut to make the ring gear, we flipped around the addendum for the dedendum, which causes this too tight fit over here. So let's start over from scratch. Let's model a new ring gear, but this time we will add some backlash, and we will also fix up the inner and outer diameters to ensure that we don't get this tip to trough interference. I've got the gear generator open again in a new blank file, and I'm going to make the same base gear as before. The difference here is that I'm going to enter a backlash of minus 0.2 millimeters. So usually if you have the normal size gear teeth and you add a positive backlash, the gear teeth become a little bit narrower. But the idea now is that by entering a negative backlash, we make the gear teeth a little bit wider. And then by doing the combined cut later on, the resulting gear teeth on the ring gear will be a little bit narrower, which corresponds to the backlash that we want. So let's click OK on this. Let's now fix up the addendum and dedendum. And for that, I will unpack this group here on the timeline by pressing this little plus. And then I'll take my history marker and roll it back by 2 positions so that it is before the circular pattern here. I'm going to take the press pull command, and I'm going to press pull this face here, and I'll press pull it outwards. And I want to point out here that under offset type, modify existing feature and automatic both will not work. It has to be new offset. And how much are we going to offset it? Well, originally it's 1 time the module for the addendum, but we want this now to be the later dedendum, so it has to be 1.25 times the module. And the difference there is then 0.25 times the module, 0.25 times 2, and then hit enter. And then we can roll the history marker back forward, and then we see that if we look at the gear teeth, only the gear tooth that we offset ourselves is lengthened, the rest is unchanged. So now we go into this circular pattern feature, right click edit feature, and then under objects we will also select this offset face that we just made, and then click OK. And this takes a moment to compute. And now we see that all of the gear teeth have been lengthened. And so now we want to fix the dedendum, and for that we'll go into the first sketch of the gear. So right click, edit sketch, and all we have to do is adjust this diameter. So the diameter that we want this to have is 112 minus 1 time the module. That is the addendum that we want to have later, which will be the dedendum now. But we want to have that on this side of the gear, but also on this side of the gear. So we'll have to do this twice. And that'll be 108 millimeters. And then finish the sketch. The final thing we can do now is activate the component to make sure that we're working inside of it. And then we'll do the sketch again. Make sure we're in the origin, 126 millimeters. And so the other way to proceed from this point forward is to take only the outer profile here, extrude it downward by 20 millimeters. And then under operation, select a new body, press OK. And then inside of the component you can remove the original body, and that will leave you with a ring gear. I've created a new bracket now, and I'm about to make the pinion. And there are two things I want to point out. First, it's important that you don't forget to turn the backlash back into a positive backlash. Second, I'm going to make this particular gear 15 millimeters thick for reasons that will become clear later on. I've set up the motion links again, and now if we take a look at it from the top, we see that we have clearance all around the gear teeth. And that is still the case as we rotate the gears around like this. A mechanism like this would be commonly used in, for example, a tower crane to slew the boom around, and it is also used in, for example, tanks to traverse the turret. What I'd like to do now is convert this mechanism into a planetary gear set. The first thing I'll do is go into the bracket and then edit this sketch. And I'm going to do a few things. First, I'm going to add an extra circle here, and I will give that a spacing of, let's say, 2 millimeters. And I'm also going to create a similar type of construction in the center here, and I'll make that equal to the shaft for the planet, and that will be the shaft to carry the sun gear. The final thing we'll do, I'll finish the sketch. We'll unhide the sketch, E for extrude. You can just press continue here. And then I press and hold until I can select the profile. And this one is coming up by 20 millimeters. That will be a join. And the other thing that we'll do is also extrude up this profile over here, this little ring. And we'll also extrude that ring over there up. And we'll extrude those up by 5 millimeters. And we'll make that a join again. And these little rings now create a little bit of a shoulder here on which the gears can ride, so that the flat surface of the gear doesn't ride against the flat surface of the planet carrier. And this at least somewhat minimizes friction and wear. And the final thing that we'll do now is go into a circular pattern. So under create, pattern, circular pattern. And then we're going to make a pattern of type features. And I want the shoulders, and I want this extrude over here, and I want to have that patterned around that center shaft. And then for the quantity, I want to have 3 planets for now. So click OK on this, and now we have 3 shafts. And the final thing we have to do now is create the sun gear. So we could just go under Tools, Add-ins, Scripts and Add-ins again, Spur Gear. And here we're going to need a sun gear of 16 teeth. It has to be 16 teeth in this case, so I'd like to go up to the whiteboard now to show you why that is the case. Here I have 2 gears in mesh, and one convenient way to think about gears is to picture them as cylinders that roll against each other without slipping. And the diameters of these cylinders then equal the pitch diameters of these gears. And this mental image will also come in handy when we talk about bevel gears. Now when looking at a planetary gear set, this actually shows quite quickly
that the diameter of the ring gear needs to be equal to the diameter of one planet plus the Sun plus another planet. But because the pitch diameter is equal to the module times the number of teeth, and all these gears have the same module, that also means that the relationship holds for the tooth counts. And going back to our example here, if we have 56 on the ring and 20 on both of these planets, then the Sun must be 16 teeth.
I'd now like to change up the joints to turn this thing into a planetary gear set. The first thing I'll do is take this bracket and rename it to planet carrier, and I will unground it, and then I will ground this component over here and I'll call it the ring gear. Now after doing this, if we rotate the planet carrier around, we see that the joints and the motion link for the planet is still fine. So what we need to do now is joint up the Sun and give that the right ratio. So I make a joint for this Sun, and I'm going to joint it to the ring gear because the ring gear is stationary. It's different if you joint it to the planet carrier because then you're going to couple a rotating object to another rotating object, which will complicate things later on. So I'm going to move this thing up by 5 millimeters so that it matches up there. And then I also need to rotate it so that it meshes correctly. And this is going to be 180 degrees divided by 16, 16 the number of teeth. And then it lines up like that. So what we need to do now is create the final motion link. So assemble, motion link. And we want to link this rotation of the planet carrier, this now has the wrong name, to this rotation of the Sun. So if the planet carrier advances 1 revolution, then that means that the planet itself has advanced by 56 teeth. And so if the planet advances 56 teeth, then you could say that the Sun gear should advance 56 divided by 16 teeth. So 16 being the number of teeth of the Sun itself. But if we do that though, we see that it doesn't quite work out. And the reason for that is the planet is not only spinning around its own axis, it's also orbiting around the Sun. And as it orbits the Sun in that way, it actually creates an additional rotation of the Sun. So it is 56 over 16 rotations for the spin of the planet, plus 1 extra rotation to account for the orbit of the planet. So we now have the beginnings of a working planetary gear set, and if we have the Sun as an input and the planet carrier as an output, we now see that the gear ratio is the number of teeth on the ring gear divided by the number of teeth on the Sun gear plus 1. So in this case it's 56 divided by 16, which is 3.5 plus 1. So this is a 1 to 4.5 gear ratio. What I'd now like to do is get 2 more planets in there because I want 3 planets. And so for this you can simply do a circular pattern, and then the type is going to be components, this component over here, and then we'll just select this axis over here. And one extra thing that I'd like to show you is that if I go for 4 planets in this case, you see that all of the planets immediately line up with the ring gear. And I'll get into that a little more later on. But going back to 3 planets, we now see that the gears don't line up. So what we have to do now is joint these planets to the rest of the model. So this planet to this shaft. Flip that back. And now it is in the correct orientation here. And I'll also do that over here. Flip it. Okay. And then to complete the motion links, the easiest thing to do here, because now the other 2 planets aren't linked, the easiest thing to do is to just motion link, not this one, I want to link that one to that one, and just 1 to 1. and I also want to motion link this one to this one also again 1 to 1. So now we have all of our motion links set up. So if we go to, for example, the sun gear rotation, so let's call this sun gear rotation. And if I now right click it and do animate model, we can see the entire gear set moving like this. And so the downside here is that every 360 degrees the entire thing resets. So that's causing a little bit of jumpiness. So one of the things you can do is, instead of that, so this is now actually the joint for the planet carrier. And if we animate this one, if it rotates a full 360 degrees, it comes back to where it started. So in this case, it is nice and continuous, but it is also pretty fast. So pick your poison in a way. And then the final thing we can do is apply some appearances. So click A for appearances. And so here we have a mostly finished model. The final thing I'm going to do to this model is create some small little cylinders for the planet carrier and the sun gear. And then also extrude this up 20 millimeters, and that just gives me 2 little cylinders that I can use to manually manipulate these gears.
Now here's the planetary gear set fully 3D printed. And what I'd like to do now is add this little indicator to the sun gear, and I'll screw that down. And I'll also make a mark on this planet over here. And what I'll do now is rotate the sun 9 times, and that should cause the planet carrier to rotate twice. 1. So as you can see, this is indeed a 4.5 to 1 reduction, or 9 to 2. And I want to point out that if you want to achieve the same reduction with a 16-tooth pinion, then you will need a 72-tooth gear to mesh with it in an ordinary gear set. And not only that, not only is it much larger, the contact here is split across 3 planets, and yet in this arrangement the contact will be just 1 gear to the next. Now the contact ratio here is higher than in these meshes here because this gear has more teeth. And the sharing of the load across the planets is never quite perfect. However, despite that, I do estimate this gear set to be about 2 to 2.5 times stronger than this arrangement here. Here I have a planetary gear set where I did not correct the addendum and dedendum. And because of this, the ring gear is now constricting the planet gears into the sun. And so if I just lift this setup by the ring gear, you see that the planets and the sun don't fall out on their own. And the unfortunate consequence of this is that if I try to rotate this gear set, I feel rather a lot of friction here and even some resistance as some of the teeth start to bind. So it's really important that you do take the backlash and addendum and dedendum into account. I'd now like to go over the requirements that you need to meet for a planetary gear set to work. The first requirement we've seen before says that the sun gear and 2 planet gears together have to fit inside the ring gear. The second requirement only applies if you want your planets to be equally spaced. So before I continue, I want to convince you that really you want them to be equally spaced. In video 2, I showed you that when you have 2 gears in mesh like this, there is a force in this direction that transmits the torque, but there is also a force in this direction that will tend to drive the gears apart. Now if we look at a planetary gear set, these forces will tend to cancel out if the planets are equally spaced. But if I take this force here and this guy here, and I move them, for example, closer to each other, we see now that the forces no longer cancel out, and there is going to be a net force on the sun that will push the sun that way. But as these planets rotate around, these forces will too, so the sun will tend to wobble around like this. and that will cause vibrations. Furthermore, if the Sun is pushed into this direction, then it will move away from these two planets and closer to this planet, which is detrimental for the load sharing between the planets. There are other configurations than just a regular polygon that will equally share the load and that will not cause a force like this, but you do have to take this into account. This gear set that we made before had the tooth counts of 56, 20 and 16 teeth. And so from this you can quite easily see that we meet requirement number 1 and number 2. Specifically, we had 56 plus 16 up here, that's 72, and divided by 3 is 24, and that's a whole number. Now, if you meet these two requirements here simultaneously, then not only do the planets fit, they will also point in the same direction. They will be in phase with each other. So for 3 planets, that doesn't work out for the gear set that I had because both of these numbers are not divisible by 3. But in Fusion 360, when I went to 4 planets, you saw that the planets immediately fell into place. And that is because both 56 and 16 are divisible by 4. I don't know if this phenomenon is useful to anyone, but it is a true fact regardless. This third requirement here checks whether there is enough space in the planetary gear set for all the planets. So when I take this planetary gear set here, I could have also selected 6 planets to comply with requirement 2, because after all, 72 is divisible by 6. But if I were to try that, I would quickly notice that there just isn't enough space for that extra planet to go in between here. And that is what this third requirement checks for. Now, I won't go into it in too much detail, but notice on the left side here that this is essentially just the outer diameter of a planet. And on the right side here we have the pitch diameter of the Sun plus the pitch diameter of a planet multiplied by this sign over here. Notice also that because the module appears on both sides of the equation, you can simply drop the module when computing it. It just makes it a little more intuitive to see what's actually going on here.
If you don't want to do math, you can also check the fit of the planets in Fusion 360 using a sketch. So here I have simply the outer diameter of a planet as the diameter of this circle. And the circle is 36 millimeters away from the center, which is the pitch radius of the Sun plus the pitch radius of the planet. So if I now create a circular pattern of this circle around the center, we see that 3 planets will fit fine, 4 planets will also fit, but in the case of 5 planets we will get interference. And going back to the math, this is the left side of the equation that I showed you before, and this distance between these 2 points is the right-hand side of that equation.
These are the gear ratios for a planetary gear set when the ring, sun, or carrier gear are held stationary respectively. So this formula here we sort of derived in Fusion 360, and the one at the bottom here is obvious to some degree because in that case the planet gears are just stationary idlers. Now it is possible that all 3 gears are rotating at the same time, and in that case you'll have to use this more general formula at the bottom. You can find more about this formula in the links below. Now, as far as I can tell, the most popular variety is to have a fixed ring gear, and that has 2 reasons. One, it has the highest possible reduction out of these 3 options, and second, by fixing the ring gear you can also fix the ring gear to the outer housing or even make it a single part, which is a lot more convenient than having the ring itself rotate around and then having another housing around it. Finally, I wish to point out that using a higher pressure angle on your gears can be very beneficial, because it will make your gear teeth stronger. The 2 downsides are that first, the force driving the gears apart like this will increase. But if you have equally spaced planets, then those forces will cancel out and it shouldn't cause you any problems. The second problem is that you will get an increased backlash. But in many applications, like driving tanks, that doesn't really matter. Finally, I should also point out that in the fixed ring case you will get a higher reduction if you have a smaller number of teeth on the sun. But you can only do that up to a point before you start running into undercutting. But having a higher pressure angle also mitigates undercutting.
Starting from an ordinary planetary gear set like this, it's quite easy to construct a helical or herringbone gear set. The first thing I'll do is remove those two cylinders that I made as handholds. So let's roll back the history marker 4 positions and then delete all features after the history marker. I'll activate the ring gear and then create a sketch on this vertical plane over here. And then P for project. I project the outer ring into the sketch. L for line. And then I'm going to look for this midpoint constraint here. And then we go up 20 millimeters. Finish the sketch and then on create, sweep, and we're going to sweep this profile along this path over here, and then we are going to enter a twist angle of 5.483 degrees, and that will give us a helix angle of 15 degrees. For the calculation on this, look back at video 3. The operation is going to be new body and then click OK, and then if we go into the ring gear, we can take this old body and remove it. So now we'll do the same to the other gears, like so. And one of the issues that I did run into is that the sun gear wouldn't cooperate with the sweep if I didn't have the hole plugged in the middle. So it would sweep it, but it wouldn't apply the twist angle. So what I did is I added this empty sketch here on the top face of the sun gear. And then I just twisted the entire sun gear profile without its hole. That being done, we can go into the separate components and remove all the bodies. So remove it from the sun and from the planets. And the planets are linked to each other, so you only need to do that once. And there we have a helical set. I do wish to point out that every sweep command here requires a different angle. So for this sweep command for the sun gear, we use an angle of 19.19 degrees, which is very different from the 5 degrees and a little bit that we used for the ring gear. Also notice that for the sun gear, the twist angle is negative. So the ring gear and the planet gears have the same handedness, and then the sun gear has opposite handedness to the rest. Finally, turning this helical gear set into a herringbone gear set is quite easy. All we have to do is activate the components. So let's start with the ring gear, and then under create, mirror this body over this mirror surface. And then relatively recently the ability came here to select operation join, so we can just click OK on this. And then it's immediately finished. We don't have to come in with a separate modify combine to join up the two halves. So that's very convenient. That's the ring gear done, so let me do the planets and the sun gear now. And that's a finished planetary herringbone gear set. All of the joints on this model are still functional, so if we go under joints and for example animate the model on the pinion, we see that everything still works fine. The only thing that is a little strange is that the planet carrier hasn't moved from where we left it. So we can go to modify move copy, and then move this guy up by, well, not 20 millimeters because we have those shoulders here, but if we move it by 15 millimeters, at least the planet carrier will line up with the planets. And then you can lengthen the shafts on the planet carriers all the way upwards if you like. So that is a completed planetary gear set with herringbone gears. Finally, I wish to warn you that if you use helical gears for a set like this, each gear will experience an axial thrust that you will have to take into account. For a herringbone set like this, you won't get an axial thrust, but assembly can be somewhat complicated. And one of the tricks people use to make assembly possible at all for a set like this is to create splits in the ring gear. So I'll activate the ring gear and then isolate it. And then I'll create a sketch on one of the vertical planes, and then I will create a projection of the trough that is directly parallel to the plane that I just selected. So project those into the sketch. It's L for line and L for construction. And then I'm going to make a construction line down the middle of this projection. And then I will use regular lines now parallel to the construction line on both sides. Next I will take these two lines and make them symmetric around the center line. And then finally I will make a distance constraint here of, let's say, 0.3 millimeters. Finish the sketch, then E for extrude. We select both of these profiles and we extrude them to distance all. And that will create a cut right down the middle of the trough here. And so this single trough allows you to take this ring gear and essentially force it open with your hands. You can also create two cuts like this, so you can bring the ring gear together like this.
That's all I have for you today. I will leave the files for this planetary gear set down in the description below. There are two more topics that I would like to cover on planetary gears. First, I would like to make a practical planetary gear set, because this one has gears riding directly on 3D printed shafts and there's no real way to mount it to anything. So I want to create a planetary gear set where all the gears are riding on bushings. Now, conceptually that's not a very difficult thing to do, but it is quite difficult to make sure that you can get all the parts in there and that you can assemble everything. And I'm hoping to mount it to a NEMA 23 stepper motor like this one, and I'm hoping to create some pretty serious torque with it. The other topic I would like to cover is compound planetary gear sets, which allow you to reach some pretty insane reductions. So a two-stage reducer could do 100 to 1 or more. Finally, I wish to point out that I've been recording the whiteboard sections of this video with my new lavalier microphone. And I'm hoping to see some improvement in the sound quality, but the main thing I'm hoping to do is to get better rejection of all sorts of ambient noise. So I used to be recording with this shotgun microphone here, or cardioid. And because that is mounted on the camera, it's a fair distance away from me, and that allows all sorts of outside noises to come in. So right now it's actually quite windy and it rains a little bit, and I can hear that quite clearly because that's all happening on this roof behind me. But I'm hoping that most of that will be rejected, relatively speaking, to the loudness of my voice. Finally, I also wish to cover at some point bevel gears, though I'm not quite sure when I'll be able to do that. This video has already taken quite a lot longer to produce than I had hoped. I've already done my first editing pass now, and it's already at 35 minutes, which is longer than I expected. So I guess there was a bit more content there than I had anticipated. With that, I'd like to thank you very much for watching, and have a great day, because I finished filming in the daytime for once.